Hello everyone, this is Dr. Vani working as Associate Professor in the Department of ECE at R.M.K College of Engineering and Technology. In this video, we are going to discuss about the fundamentals of information theory, which is the first unit in digital communication. Now, before getting into information theory, we need to understand its importance. So if we take a basic communication model, the first block is the information source, which is generating the information represented as message. This message may be audio, video, text, or any image. It has to be represented in efficient way. So information theory plays a major role here to represent this information, right? Then the messages are transmitted by the transmitter and received at the receiver, where it is again decoded. So today in this video, we are going to see how information theory is defined, who is the father of information theory, what is the relationship between uncertainty, probability, and information, properties of information. Also, we are going to see the types of sources and entropy and its properties. So, Mr. Shannon, who is called as the father of information theory, invented these mathematical concepts in 1948. This theory studies the quantification of information, how to store information, and how to communicate this information. It also uses probability theory. This mathematical theory forms the foundation for data compression, digital computers, digital circuit design, cryptography, artificial intelligence, and human-computer interaction. So it shows the significance of this information theory. So we are going to understand the relationship between uncertainty, probability, and information. By taking an example, we can understand the relationship. The first statement, tomorrow the sun will rise in the east. It is a certain event, right? Definitely it is going to happen. So what is the information content in that? I'm not conveying any new information to you. So the information content is 0. Probability of occurrence of this event is maximum, which is 1. And it is a certain event. Second case, second example, if I take, the phone will ring in the next 1 hour, right? So it may ring or may not ring. So the probability, if approximately we take 0.5, then there is some information, some new information I'm conveying to you, right? And it is an uncertain event. It may happen or may not happen. Third case, it will snow in Chennai this winter. Again, this may happen or may not happen. So the probability of occurrence may be 0.4, 0.3, right? So when the probability is less, I am conveying new information to you, and also this is an uncertain event. So from these three examples, how does uncertainty relate to probability of occurrence? More uncertainty, probability of occurrence is less. Similarly, how does information relate to probability? More is the probability of occurrence, less is the information. On the other way, if the probability of occurrence is less, the information content of the event is more. So the relationship shows that information and probability are inversely proportional. Now, generally there are two approaches to define particular event. So one is the intuitive approach in probability. So the information contained in a statement is inversely proportional to the probability of occurrence. We have seen the three cases here. More uncertainty leads to more information. So that is intuitive approach from the above three examples. But mathematical formulation is very important in order to frame information theory. So the amount of information I is given by log of 1 by p, which means it is inversely proportional to probability of occurrence. The base of this probability may be 2. The base of this probability may be natural units E. Okay, so based on this intuitive field, occurrence of a less probable event conveys more information. So this is called as self-information. If I consider a discrete random variable x with possible outcomes xi, where I is varying from 1 to n, then the information of xi can be given by log of 1 by p of xi. By applying the rules of log, this can be taken out with minus. So minus log of p of x of I, which is the fundamental relationship between information and probability. Now let us take an example. Consider a binary source which tosses a fair coin. The output may be head or it may be tail. Suppose I am taking equal probability of head and tail, then probability of 1 is equal to probability of 0 is equal to 0.5, right? So if I apply this to the information formula, I am getting minus log 2 of 0.5, which is log 2 of 2, which is equal to 1. Right? So this is actually 2 power minus 1. This minus 1 and minus will become 1 bit. So we have to use only 1 bit to represent the output for the output from the binary source. Okay. Now here comes one important concept, why we have to use log scale. So here we have assumed independent events. So in independent events, when we are representing in terms of probabilities, it will multiply, right? So similarly, if I am getting information from multiple sources, I would like to add to all the information to obtain the total information. So obviously which is the mathematical operator which will convert the multiplication of probabilities into addition? The only answer is log, right? So that's why when source A is also tossing a coin, source B is also tossing the coin, the total information in this case will be information of A plus information of B. Hence log scale is used. Next comes classification of sources. A source with memory uh, is called as memory source, or for example Markov source. Another source is memory-less source, discrete memory-less source, which will not depend upon the previous symbol, while the source with memory will be depending upon the previous symbol also. Example is Markov source. And the example for memoryless source is outcome of tossing a coin at particular instant of time. Now again, in order to understand the importance of probability with information theory, let us consider an example. So in a binary PCM, if 0 occurs with probability of 1 by 4 and 1 occurs with probability of 3 by 4, then calculate the amount of information carried by each unit. So we can apply the formula. P of 0 is equal to 1 by 4, P of 1 equal to 3 by 4 are the given values. So information I is nothing but equal to log 2 1 by P of 0, which is log 2 of 4, log 2 square, so which will become 2 bits. Similarly, the other bit 1, the number of bits is equal to log 2 1.33, which is equal to 0.415 bits. So what is the significance of this equation? If we see the significance, when we are saying probability of 1 by 4, the less probable event is represented by more number of bits, while the more probable event 0.75 is represented by less number of bits. So again, this quantifies the information theory with respect to probability. Properties of information. If the outcome of an event is certain, then no information is gained. That is, if the probability of occurrence of certain event is 1 maximum, then no information is conveyed. So information will be equal to 0. That is the meaning of first property. Second property, if the probability lies between 0 and 1, obviously the information there, if it is 0, then maximum information. If it is 1, then no information. So information is again inversely proportional to the probability. That is the second property. Now, third property, less probable the event is, more information gained. If we are comparing two events, one is less probable, then it will contain more information. Last property is summation of two information, that is Sk and S1 are statistically independent, then the total information will be summation of individual information. So these four properties plays a major role while applying information. Next comes entropy. Actually, so far what we have discussed is self-information, information contained in particular event. Now we are going to discuss about average information content. That is the expected value, which is the sum of self-information of each outcome weighted by the probability of each outcome occurring. This can be better understood by taking an example. That is, the quantity h of s mathematically represented by summation of k equal to 0 to k minus 1 pk I of sk, where I of sk already we know it is the information, right? So it is log to 1 by pk. So the entropy of a discrete random variable represents the output of a source of information, which is a measure of average information content per source symbol. So again, this mathematics can be understood by taking an example. Suppose we are taking a political poll. Obviously, the outcome of the poll is unpredictable, right? So performing the poll and learning the result gives some new information. Obviously, we are not aware what will be the result. So the entropy of the poll results is large. The average information content is large. This is the case when we are doing the political poll for the first time. Now, same poll is performed a second time shortly after the first poll. Now we are knowing about the previous results. So the outcome of the second poll can be predicted well. We will not have much information. So entropy of the second poll result will be less compared to the first. The average information content will be less compared to the first. Now, properties of entropy. Entropy of discrete random variable is bounded between 0 and 1. The meaning is entropy is 0 if probability of occurrence is 1, that is no uncertainty. At the same time, it will have maximum value for equiprobable and maximum uncertainty values. Right? So these are the properties of entropy. Entropy plays a major role in order to understand the data compression also. How much the data can be compressed. That information is directly proportional to entropy. So entropy plays a major role for multimedia compression techniques. As a summary to this video, we have defined what is information theory, which is nothing but inversely proportional to probability of occurrence. We have seen further of information theory. We have found out the relationship between uncertainty, information, and properties of information. Also, we have seen types of sources with entropy and properties.